Excellent. Okay, so our next speaker, I guess, is Jeff Gillis-Davis, who will be speaking about lunar regolith surface features as indicators of volatile release.
Hey.
Okay. So can you see that all right, my full screen?
Looks great, thanks.
Okay, great. So yes, today I'd like to present our research on looking at lunar regolith features and seeing some evidence for volatile release in them. So this all stems from evidence that has come out in the last 20 years from radar, albedo, impacts, and neutron spectrometer data that all show that there is water at the poles of the moon. And then with the L-cross impact, that shows us that it's not just simply water ice, but it's actually a very complex mixture and makes it even an interesting story, even more interesting. But the big question, at least in my mind after that, is, well, how did the water get there? And the origin story for water, as Paul Lucy illuminated about 30 minutes ago, is, three of the main reasons are thought to be solar wind protons, volatiles released from volcanic activity, or delivery from comets and hydrous asteroids. And Paul, I think, maybe dismissed solar wind protons as a source, and that's what I want to show today in the rest of my slides, so I'm glad I get to go second. So the premise here is we did some experiments a couple years ago, taking some olivine, irradiating them with deuterium. That helped us make sure that we were making heavy water that came from the experiments and not any kind of contamination. When we did our experiments without heating, we didn't see any evidence for water coming off the samples during the experiment or during the temperature programmed absorption or heating. But we hit the samples with a laser, as you can see on the right, on the top here, after irradiation to 10 to the 18 ions per cubic centimeter. We irradiated it with a CO2 laser when we heated it, and that was to simulate micrometeorite impacts. We were able to release D2O, and when we stopped the signal, at least of the D2 stopped, and also D2 would start to go down. And we're like, well, okay, we're at least now making water, but what does it look like on the samples? So we looked at the samples under SEM. So these two images, A and B, are SEM secondary electron images. And what you can see on image A, about halfway through, there's kind of a shoreline. On the left-hand side of that, there's some radiation expansion that happened. And within that, in the right image, we zoom in, and you can see there are these little vesicles. Some of them even have popped over lids. And it's like, okay, great. This is how the water is escaping. It seems to be happening in kind of little catastrophic events. So those vesicles are only about a half micron or so. But does this actually happen in lunar samples? So we decided to look at some, and on the left, we have Neil Armstrong collecting our sample 1084. On the right is what it looks like when we put it on a SEM aluminum stub. And it's about half centimeter across. And you can see that we have about 100 grains laid out there. Now, when we looked at these under moderate and high magnification, we could see pits in different grains of sample. And we classified them into 4 types. We have bowl-shaped pits and small irregular pits in that first image, with these guys here being the bowl-shaped pits, and these are the smaller irregular pits, and we'll take a closer look at those. We have larger irregular pits like this guy here in the middle image with the arrow pointing at it. And then these circular, what we call bottomless pits, and these are only found in agglutinates. And they also have these kind of rims that almost look like they could be impact, but it seems to be caused by the process as it degasses. So looking at these a little bit closer, this is an impact melt-glass speed, which we know from its composition when compared to Delano 1986. And we're looking straight down at this glass bead. It's actually oriented about 45 degrees. And when we tilt the stage about 90 degrees, you can see here are our bowl-shaped pits, the type 1 pits at both ends. And then you might be able to make out these very fine, small speckled pits, the irregular small pits along the body of it. We're going to zoom into this location next, just to kind of see the two in comparison. So orange arrow here points to our type 1 pits, the bowl-shaped pits, which are about 2 microns across. And then the blue circles in both cases show us the type 2 small irregular pits, which are only about a 0.5 micron. And the next image, we're going to go and look at the grain on the other side. And what you're seeing here is at the top right-hand side is actually a zap pit or a micro pit from a impact crater, a microcrater, and it sheared off this side of the grain. And we find that the pits, the large pits, seem to be mostly antipodal to this impact, and also just adjacent to the impact on the other side. Unfortunately, we've kind of lost this part of the crater. But these pits look a lot like what we see in the experiments that we did. We did some TEM analysis of these pits, and you can just see, the bowl-shaped pit, even at this scale of a couple hundred microns, looks like a bowl. Up top is a bright field image, and then down below is a HADF or dark field image. So carbon and light elements are dark in the HADF image, and you can see a nice profile through the image or through the crater. And then these, again, are bright field and dark field images, top and bottom. The SEM picture at the bottom shows the 1, 2, 3 pits that we intersected, and you can see they kind of looks like a nook and cranny of an English muffin on top there. They're, very irregular and a lot smaller. So it suggests it's probably a different formation mechanism. Now looking at some of these type 3 pits, the larger pits. This again is another impact melt grain that we're looking at. We're going to zoom into that box. And here's what the irregular pits look like on top and bottom on the left, and a little zoomed out image on the right. And you can see it's a little bit nicer looking than the irregular pits, but not as bowl-shaped as the bowl-shaped pits. And then moving along to the type 4, we're going to see that a zoom in from this left image, a higher zoom in the middle, and then an even higher zoom on the right. We see these holes that are in the melt glass themselves, which suggests that we're releasing volatiles either from the melt glass itself, or perhaps the blob of melt that landed on this grain actually heated the sample enough to release any volatiles that were contained in the sample. Then this is another image of a type 4. Again, we're zooming in as we go from this time right to left. So on the far right, you see what looks like a nice agglutinate, which is just a melt welded grain that holds together pieces of all types of little rocks, melt grains, and
Mark.
Thank you. And as we zoom in the middle image, you can see a melt blob that's on the top kind of middle part. It got cross-sectioned, and you can see how vesiculated this melt is, much like agglutinates are known to be. And as we zoom in further, and then finally to the bottom, you can see where the melt was sticky enough where when gases came out, you form this kind of lip or rim around the holes, which suggests it's happening over time. Some of these holes have very sharp rims, and then some, after maybe a little bit more cooling, gets these kind of lips or rims to them. But it shows how this pit is probably just an intersection of one of these bigger vesicle voids within the melt. And in this last conclusion, here's another impact melt glass with an impact again in itself. You can see it's got a lot of radiation blistering in some of the small pits, but we don't see any of the larger pits on this. So in conclusion, the type 1 and our type 4, the bowl shape and the bottomless, are evidence of some kind of volatile release. It's either like a 1-2 step process where we have solar wind implantation. It gets stuck in the samples until it gets released by an impact heating event, like our experiments suggested, or some nearby melting, which is kind of like the DeSimone Orlando model. Or the pits might actually be created by volatiles supplied by the impacts, which is kind of interesting if we could get some trapped gases from these. The type 2 small irregular pits might be produced by very low thermal events. These are found ubiquitously over many surfaces, and it could be some evidence, physical evidence of recombinative desorption. And then finally, the type 3, the larger regular pits, they might be bowl-shaped pits degraded by space weathering, or maybe even impressions made while the melt was hot. You know, we see, like in the image on the right, sometimes stuff can actually get stuck in the melt. So that's all I have to present today. TGIF to everyone, and thanks for a great meeting.
Thanks so much, Jeff. We have a question that came up from Tom Orlando asking whether you can confirm that the electron beam in the SEM is not contributing to this. And then he also asks whether you had time-dependent studies to look at if the pits change, mentioning that this could involve a classic radiation damage process.
I think Tom's question is probably mostly focused on the experimental samples, so that's how I'm going to answer it. We didn't see any change with the pit or creation of any pits while we were looking at these samples with the SEM. We are aware that it is possible to damage and heat these samples up. So we were using low voltage and a wide beam. So we don't think we made it. What was the second? Oh.
Okay. Yeah, you have some more questions coming in the chat you might want to look at.
Okay.
But I think we'll go ahead and start the next talk.